Good afternoon. My name is Hashmi. I'm a first year PhD student at the University of Nottingham in the UK. Today I will talk about my research about um, ultrasonic temperature sensors. Okay, so that's my presentation outline. I will start with some introduction about ultrasonic thermometry, and then there will be some comparison about some comparison between different architectures of ultrasonic temperature sensors. And there will be some background about how I measured the frequency of the ultrasound, and then the use of bandpass filter in the loop, and then I will talk briefly about the PSOC which is the microcontroller I used in my project and research, and then there will be some conclusions. So first of all, we can use the ultrasonic NDE, non-destructive evaluation sensor, in order to measure different physical quantities, such as density, viscosity, and temperature. And our question here is why we use the ultrasonic temperature sensors over the conventional temperature sensors. So first of all, ultrasonic temperature sensor can sense the temperature across the complete pathway, whereas the conventional temperature sensor can only sense the temperature at single points. So, for example, if we want to measure the temperature across this room, we can use just one pair of ultrasonic sensors in order to get average temperature. And the second advantage of using ultrasonic sensors is it's fast comparing to conventional sensors. So we found that ultrasound travels 1 meter in water in only 7 milliseconds. But for conventional temperature sensors, they need between 2 to 3 seconds in order to calibrate. So they need to be calibrated between. There should be some thermal equilibrium between the sensor itself and the medium, and they can potentially produce high resolution measurements. So in our application, we achieved a resolution of, worst case scenario of 100 ppm, and and the and the sensitivity of temperature is about 1000 ppm per degree centigrade. So our resolution for this sensor is about 0.1 degrees Kelvin, which is much better than the available inexpensive conventional temperature sensors. So here I'll talk about different architectures of ultrasonic temperature sensors. In this discussion, I will consider temperature measurement of water through transmission evaluation of one pair of ultrasonic sensors, and then this measurement based on the fact that ultrasonic velocity is dependent upon the temperature. I will cover these 4 different architectures. The first one is direct time of flight measurement, and single round architecture, phase shift measurement, and oscillating architecture, which we are using in our experiments. So first architecture is called direct time of flight measurement. So we have here the transmitter and receiver, and in this area will be the medium, which is the water, and then we have to use an amplifier to compensate for energy and conversion loss when the signal travels through the water, and then we have this delay estimation block, which measures the time difference between the instances of detection of the excitation pulse and propagated pulse. There are 2 disadvantages of this method. The main objective of our development is to design an expensive device. In this case, we need a clock frequency of about 150 megahertz, which is a bit difficult to achieve using inexpensive equipment. And in this case, we achieved some or we face some potential jitter and uncertainty due to the additive noise of the signal. One of the examples of one of the applications of this method is the cross correlation processing. When measure or estimate the time of light based on the instances of center of mass gravity between two objects. The second architecture is called single-round architecture, which involves recirculating pulse. So in this case, we circulate a pulse for given intervals, and then the time of light should be the time over the number of intervals. We will face here the same disadvantages, which will result in potential data intensity due to additive noise. The third architecture is similar to the first architecture, but in this case, we feed the input with sinusoidal signal with non-frequency. So the time of light should be now function of this given frequency, and the phase shift between the transmitter and receiver at this point. And we face the same problem about the cost. We need even higher clock frequency, more than 150 megahertz, in order to implement this method. The fourth method which we are using now is called oscillating architecture, and it's very attractive due to its simplicity. It only requires a single amplifier between the transmitter and receiver of the ultrasonic transducer, and they feature shorter measurement time comparing to previous architectures. However, using inexpensive ultrasonic transducer will result in unwanted harmonics. So this requires us to implement a bandpass filter in order to remove these harmonics when the signal travels through the water. So the cost is one of the important factors of our projects, because we try to minimize the cost. So the price of wideband high frequency ultrasound transducer costs around $100. But for the transducer we are using, it's narrow band low frequency ultrasound transducer, which costs around a few dollars. And the cost of support electronics could be high, but in our project we used a system called programmable system on chip, which was introduced by Cypress, which integrates some analog and digital features of the circuit. So as I mentioned, most inexpensive ultrasonic transducers feature several resonances, and they can oscillate at different frequency at different times. So that's a call for development of bandpass filter. So a robust design using this architecture should be included. This bandpass filter integrated in these PSOCs operates based on switch capacitors, and one of the most important properties of these filters is that they can be adjusted during the operation runtime. And using one single chip that includes the bandpass filter and amplifier would reduce the cost. So in order to have oscillation, there is one important, very important condition that should be met, which is the overall gain of the oscillator should be higher than 1. But however, when the signal exceeds, or the gain exceeds unity, the system goes to saturation, and we found that when the system goes to saturation, there will be a lot of scatters of frequency measurements. So we used the programmable gain amplifiers implemented in this PSOCs. We can program up to 4 PGAs inside one PSOC, and there is a wide range of available discrete gain settings, and we can cascade these amplifiers. So this picture is actually one of the figures in our paper that shows the frequency value of ultrasonic transducers versus the gain component of two cascaded PGAs. We fixed the first values of the amplifier, and we fired the another one. So as you can see in this picture, our system is highly highly nonlinear, and we can see even for the same combination of gain, we can get a deviation in temperature of about plus or minus 10 hertz. So at the beginning, we've chosen a point that we ensured maximum flatness, so the signal is not deviated by this amount of frequency. But this selection can be only made for single frequency, and due to the aging properties of piezoelectric elements, that called for a development of automatic gain control. So we had three ideas to implement this automatic gain controls. First of all, the comparators. We can use a comparator to control the upper and lower limit of the signal and program the amplifier based on these parameters. And then we had an idea of using a filament light bulbs when we can control we can control the gain for the nonlinear current and voltage characteristics. And that's our final design of automatic gain control. So we have three stages of amplification. The first one is using the first method, which is about comparator. So when signal travels from point A to B, a signal at point B should be high in order to have an optimum level for the next AGC to work. And the AGC between point B and C is JFET based amplifier, and the signal at point C should always be the same. And then that's a fixed amplifier to have a voltage in this level between the voltage rays. So that's one of the potential applications of our project, which is about using it to measure the power loss of water-cooled electric motors. So that's the experimental setup. Water-cooled, the power loss of water-cooled electric motors is a function of the temperature difference between inlet and outlet of the water jackets and the water heat capacity and the flow rate. And we designed this chamber to be inserted at the inlet outlet, which features 4 pairs of temperature sensors, ultrasonic sensors, and 16 conventional sensors. I'll just jump to the results. So that's the result. Our result obtained from experiment. So the green curve is the temperature, and the blue curve is the ultrasound frequency. And we can see that the frequency follows the temperature, and there is a consistency. But when we try to plot the frequency versus temperature, we found that there is a hysteresis effect, and we found out that the hysteresis is one of the properties of piezoelectric materials, and we will try in future to tackle this problem either by apply some signal processing or to employ data sensor fusion, when we can use different types of sensor in order to correct each other. So in conclusion, we can say that ultrasonic temperature sensors offer several attractive features that are not available using conventional sensors. The developed oscillating temperature sensor demonstrate appropriate sensing behavior at a reasonable cost, around. So the overall cost of the project around $6 or $7. We reported that recent development that enabled better control of the sensor's operation and behavior. A limited number of low-cost electronic components showed notable improvement over previous designs. And despite behavior of the presented experimental temperature curve, we faced some hysteresis that we plan to address in future. Thank you very much.